Three-phase AC induction motors use magnetic induction to convert three-phase AC power into mechanical energy. They're used throughout industry to drive equipment such as pumps, compressors, and fans. Three-phase AC induction motors are economical, efficient, and reliable, but even the best equipment may still break down. Since your job includes maintaining three-phase motors, you need to be thoroughly familiar with these types of motors. In order to understand how a three-phase AC induction motor works, you first need to understand the basic principles of alternating current and three-phase AC. So far, we've been looking at single-phase alternating current. Three-phase alternating current is actually three separate alternating currents. The three currents are very similar, but they're produced at intervals. In other words, they're out of phase. Each of the three phases flows through a separate conductor. In reality, all three currents are generated at once, but we'll look at them individually to get a better idea of what's going on. In this part, we'll identify the parts of a typical three-phase AC motor, and we'll look at two common types of these motors. We'll also see how a three-phase AC motor operates. When three-phase alternating current flows through each coil pair, a magnetic field is produced between the coils. The strength of this magnetic field changes as the current increases and decreases, and the magnetic field's north and south poles reverse when the current changes direction. We can use the stator illustration to see how the magnetic field is generated and how it rotates. In this example, we'll use colors to represent the magnetic field. Green is north and yellow is south. We'll also slow the speed of the rotation down to better show what it looks like. When the first coil pair is energized, current flows through it. This current produces a magnetic field between the coils. The magnetic field changes with the current, and its north and south poles reverse with the changes in current direction. The same is true for the second coil pair and the third coil pair. As current flows through each coil pair, the strength of each magnetic field produced changes as current increases and decreases. The north and south poles reverse when current changes direction. The magnetic fields produced by the three sets of coils merge to form one overall magnetic field. For example, this is a representation of the polarity of the overall magnetic field between the stator coils when the first phase current is at its maximum. This is the polarity of the overall field between the stator coils when the second phase current is at its maximum. And this is the polarity of the field when the third phase is at its maximum. The net effect, through the complete three-phase cycle, is that the overall magnetic field between the stator coils rotates. The speed at which the magnetic field rotates depends primarily on two factors. One factor is the frequency of the current, that is, how many times the current cycles each second. The greater the number of poles in a stator, the slower the rotation of the stator's magnetic field. And the slower the rotation of the magnetic field, the slower the rotation of the rotor. So, a motor may be selected to drive a particular load based on how many stator poles the motor has and how fast the load needs to rotate. Now that we've looked at the magnetic field produced in the stator of a three-phase motor, let's see how this brings about the rotor's rotation. Whenever there is a relative motion between a conductor and a magnetic field, a voltage is induced in the conductor. Here's the rotor of a three-phase motor in the rotating magnetic field of the motor's stator. The rotor contains conductors, so the relative motion between the rotor and the stator's rotating magnetic field induces a voltage. The induced voltage creates a flow of alternating current in the rotor's conductors. So as the stator's magnetic field rotates, the current flowing in the rotor produces a magnetic field that expands and collapses as the current in the rotor alternates. The rotor's magnetic field interacts with the stator's magnetic field, causing the rotor to turn in the same direction as the rotating stator field. There is also relative motion between the rotor's magnetic field and the stator's coils. As a result of this relative motion, the rotor induces a voltage in the stator. This voltage increases what is called the effective voltage in the stator. Effective voltage is the voltage that actually exists in the stator at any given time. The three voltages combine into a single effective voltage that causes current to flow in the stator. The three individual voltages are important because a change in any one of them causes a change in the effective voltage. The effective voltage in the stator of a three-phase motor is greatest when the motor is first started. When the motor is first started, the stator's magnetic field is rotating at a high speed, but the rotor is just beginning to turn. The difference between the speed of the rotor and the speed of the stator's magnetic field is maximum. That causes the rotor's magnetic field to change rapidly. The faster the rotor's field changes, the greater the voltage induced back into the stator. Therefore, the voltage induced in the stator by the rotor is at its maximum when the motor is started. This makes the effective voltage high when the motor is started and results in a high starting current. If an ammeter is connected to the motor, we can see the high starting current when the motor is first started. As the difference between the speed of the rotor and the speed of the stator's magnetic field gets smaller, less voltage is induced in the stator. So, the effective voltage decreases and current decreases. Now, there is always some opposition to the rotor's rotation. It usually comes from friction within the motor, the load the motor is driving, or both. This opposition causes the rotor to turn more slowly than the stator's magnetic field, so that the rotor's rotation never reaches the exact speed of the rotation of the stator's magnetic field. This means that there is always some relative motion between the rotor and the stator's magnetic field. The speed of the stator's magnetic field and the speed of the rotor are related, even though they're not equal. If the speed of the stator's magnetic field is cut in half, the rotor's rotation slows by approximately half too. The difference between the speed of the stator's magnetic field and the speed of the rotor is called slip. Slip is often expressed as a percentage. The amount of slip found in various induction motors varies, from approximately 5% to about 13% slip depending on the motor. This means that the operating speed of the rotor is about 10% slower than the speed of the stator's magnetic field. Slip also determines the amount of voltage induced in the stator by the rotor. The greater the slip, the greater the effective voltage in the stator, and the greater the amount of current in the stator. For example, when an increased load is placed on a motor, the rotor slows down. When slip increases, more voltage is induced in the rotor by the stator's magnetic field, and the current flow in the rotor increases. Because of this increase in current flow, the rotor's magnetic field gets stronger. The rotor turns more strongly, and the motor produces more mechanical power. At the same time, the effective voltage in the stator increases. This increase in voltage causes current to increase, and the electrical power that the motor is using also increases. In this part, we'll look at how the speed of an AC motor can be controlled. One way speed control can be provided is by using sophisticated electronic devices and specially built motors. Another way to provide speed control is to construct motors with more stator circuits, each with different numbers of poles. The speed of the motor's rotation is determined by how many poles are in the circuit that's energized. When a motor is well cared for, many major problems can be avoided. Certain routine measures can be taken and maintenance performed to keep problems from occurring and to ensure a motor's continued performance. Motor inspections are done to detect minor problems before they become major. This part of the program looks at how operating and non-operating three-phase AC motors can be inspected. Before inspecting a motor that's operating, you need to take safety precautions, such as putting on any required personal protective equipment. The inspection begins with a visual inspection for any loose or broken parts. The motor's air vent should be checked for dirt, grease, and other obstructions to airflow. This airflow through the motor provides cooling for its internal parts. Also, listen to the motor. A motor that's operating correctly should have a smooth, steady sound. An unsteady sound or an increase in motor noise could be an indication of motor trouble, such as an electrical fault or a bearing failure. Unusual movement of the shaft or vibration of the motor can also be an indication of motor trouble. Unusual movement of the shaft or vibration of the motor could be caused by shaft misalignment, an unbalanced load, or worn bearings. Vibration can be felt as well as heard, so it's a good idea to touch the motor carefully to locate the area of greatest vibration. First, to help make sure you won't be shocked, make sure the motor's grounding strap is attached before you touch the motor. You must use extreme caution when touching the bearing housings. If there's a problem in this area, there may be enough heat to burn you. Some motors have instruments installed in them to measure temperature and vibration. For other motors, you may need to use a vibration meter to measure the motor's vibration, and a contact pyrometer to measure its temperature. Regardless of the instruments that are used, the readings you take should be compared to previous readings taken under the same conditions to see if a trend is developing. A trend toward increasing temperature or vibration, or both, may be a sign of a problem that will cause a motor failure in the future. A trend of increasing readings should be reported to a supervisor. If the motor you're inspecting is a wound rotor motor, pay special attention to the slip rings, the brushes, and the brush rigging. All of the brushes should be touching their slip rings. Brushes that are worn can be replaced after the motor has been stopped and locked out according to approved procedures. The current flowing to an operating motor should be checked for balance between phases. A balance between the phases means that the current in each phase is the same. If the phases are not balanced, the motor will not run efficiently and could become mechanically unbalanced. Some large motors have built-in ammeters. If the motor you're inspecting does not, this check can be made at the Motor Control Center. Access to the motor line leads and controls is attained by unfastening the front of the control center's enclosure. These three conductors supply the motor's power. A clamp-on ammeter can be used to check the current flow in each of the three conductors. If the three-phase currents are not the same, there is a phase imbalance.